So this construction is something that I learned on a site called Geometricon by Pamfilos. You can see here the page. So in this page here, Professor Pamfilos, he says the following: if you start with 3 points A, B, C on a parabola, okay, and you know, say the axis of this parabola, okay, then you can simply calculate or construct the anticomplementary triangle A prime, B prime, C prime, and then lift these red lines, lift or lower these lines parallel to the axis, and they're going to meet the opposite sides of the anticomplementary triangle in points A prime prime, B prime prime, and C prime prime, which also lie on the parabola. Okay, so I'm actually playing around with this idea. This is quite to me, I wasn't aware of this, and I think this is quite beautiful. Let's start with this blue triangle here. Okay, 1, 2, 3. And I have some controls on the right here where I can actually play with the X location, for example, of the first vertex here of my blue, or I can play with the X location of the second vertex of my blue, or the X location of the third one. So I can basically choose an arbitrary parabola-inscribed blue triangle. And then I'm showing here as well the anticomplementary triangle. So the dashed blue guy is the anticomplementary of the reference blue. And then I'm doing exactly Professor Pamfilos' construction. I'm going to take each one of my anticomplementary vertices and draw a line parallel to the axis of the parabola. Here's the focus, to the axis of the parabola. And I'm going to mark off a vertex of a new triangle where that line intersects the side opposite on the anticomplementary to this particular vertex. So I'm going to draw this line here, intersect my opposite side, and say, okay, this is a vertex of my new triangle. I'm going to do the same here for this guy. I'm here intersecting an extension of 1, 2, I believe, no, an extension of this long side here that is going to fall over there, okay, of the anticomplementary. And here I'm actually taking, so this vertex 2 here, I'm intersecting at point 3 of the green, this particular opposing side on my anticomplementary. Now what this simulation shows is a third triangle, which is naturally associated with blue, which is its polar image with respect to the parabola. So I'm showing here an orange triangle whose sides are tangent to the black parabola at the vertices of the blue. So this is sometimes called the polar with respect to this conic, this parabola. And we can see dynamically here that for whichever inscribed blue triangle I choose in the parabola, this construction is going to produce a green triangle, okay, which is both similar to the polar triangle and with 16 times its area. Okay, so I'm showing here numerically that the ratio of areas of the green triangle divided by the orange triangle is 16, and that their sides are parallel. So I just wanted to submit this as a note to Professor Pamfilos' beautiful construction, and I thought this was a cool way to generate a homothetic copy of the polar triangle.